from very big science to very small science. In fact, I'm purposely going to start with kind of the smallest, silliest, most trivial experiment we did, but show you where these things can lead. And also with only 3 shuttle flights left, I really wanted to focus on the human side of human space flight and kind of weave in, as Noel started, with some of the backstories behind a lot of these experiments. So what I'm going to go through on behalf of a lot of colleagues is work that's been done in combustion, in fluids, in material science, and some of the biotechnology. And I'll try to, I have to lower the lights to just make it easier to see these movies and not as easy to see me. All right, so I said, start with the most trivial one. Started in a hallway conversation at a drop tower. Would a candle burn in 0G on the shuttle? Conversation with me and a couple grad students. We completely disagreed. Found out that it was on at least 6 different, from MIT to Stanford. It had been a question asked on PhD dissertation, exams, answered differently by experts around the world. And we said, wonder if we can sell this as a simple high school education experiment, when in fact we didn't know the answer ourselves, which we did. And since it was so early in the game, on STS history, we'd flown so few combustion experiments, they made us put it in a Lexan non-flammable box where we could drill some holes in it, had a hot wire igniter, and away we went. Had no idea on the photography, etc. But what we found was, as you might expect, a round flame, except near the bottom where the candle wax itself quenched it. You don't see any of the yellow, which is soot, because it's a lower temperature flame than could do it. And it burned for about 45 seconds, which we had a bet going amongst all of us. I lost. I had 20 seconds. But we realized that that was about the time where it would kind of use all the oxygen inside that Lexan box. So would it have burned longer if we actually had another chance? So we got on the mirror. And they let us switch from this Lexan box to a wire mesh, which had much more open. By the way, we looked at 2 candles in opposition to each other. And once you light one, you can't light the other because all the oxygen's been used, which was sort of, again, unexpected. But the Russians required us to fly oxygen sensors with it, so we used, just to let us on board. So we used these commercial off-the-shelf sensors. They didn't work worth a darn in flight, but it got us on the mirror. So they drifted, they were incredibly temperature sensitive, and basically ended up a piece of junk in orbit. Well, what we learned when we actually got rid of the box is that this candle that burned for about 10 minutes, and here on Earth, instead of 45 seconds, it went up to 45 minutes. An incredibly weak flame, but it could survive a very long time. We asked the crew members to turn the lights on and off. So like the old Karate Kid movie, wax on, wax off, lights on, lights off. And what we found is all the wax had melted, but it didn't drip off, okay, because there was no gravity pulling it down. Inside that wax melt was these incredibly fast thermocapillary driven flows going round and round. Aerosol sprays coming off here, which turned out later to be important. And early on in the lifetime, it did have some soot. Okay, so that, at the end of one of the mirror experiments, again, this all started with the shuttle, Shannon Lucid turned on the lights and said, I see a dandelion there, sitting there. And this was right after the flame went out. And if anybody knows mirror, you had 10 minutes of comm time, 70 minutes of no comm. And right at the end of her comm, she said, can you tell me what that is? And suddenly all the lights lit up from Moscow over to us. What is that thing? And it turned out, in the 70 minutes we had, we figured out that that's probably flammable vapor that had, once the flame went away, had condensed kind of into a nice little round ball of flammable material. So we told her, turn on the fan inside the glove box where this was operating, blow it all against a filter, and it'll safe the whole thing. It was actually informed us on if there ever is a fire, on a spacecraft, that you got to worry about the post-fire operations even after the fire's out. All right, so I mentioned the oxygen sensors that didn't work. They said we'd have another chance to fly, and we really wanted to know what the oxygen concentration was ourselves. Since we couldn't find the ones that would work, that were really, really small, wouldn't hurt this delicate flame, we built our own oxygen sensor, CO2 sensor, using infrared absorption and some fluorescence quenching. Proved that they wouldn't drift, could sample very, very fast. Got all set to fly, couldn't, and then the flight got canceled. So in sitting around, what do we do with this stuff? Somebody said, boy, you need to know oxygen concentration and CO2 concentration for doing metabolic analysis during exercise. And these things are really small. So wonder if you could integrate them into a mask, okay, which we did. The portable unit for metabolic analysis, or PUMA, oxygen, CO2 custom sensors that were our own, pressure, temperature that were COTS and modified just flow device. And got permission to test it in a pediatric cardiology lab and an exercise physiology lab. All self-contained electronics, wireless transmission back to any permanent recording device. Fast forward this continuing through a number of years. Got it tested on Nemo. It worked at 2.5 atmospheres, underneath. Have shown it to several flight surgeons, have yet to get it on board the space station. We think this will work as well or better than what's planned, what's up there now, but we'll see. I mean, there are arguments on both sides. But here's the end of this. The end of this story is that the Navy got interested, and it has been successfully used for testing O2, CO2 concentration, and again, all the other things, metabolic analysis, testing for hypoxia in pilots, Air Force pilots flying at high altitude. Okay, so you start this story with, will a candle burn in 0G, and you end up 18 years later at testing Air Force pilots at high altitude. Along the way, you publish this little stuff in Scientific American, Popular Science, our combustion journals, et cetera. So it's fun to see where experiments will lead. I'm going to switch. There's a bunch of very practical combustion experiments. For time, I'm not going to go into them. Fluids is now the next area. Lots and lots of cover stories that were done. One topical area is just colloids. Colloids are simply the small particles that float around in paint, shampoo, soap, detergent, milk, fabric enhancers, etc. It's more than $100 billion industry. It's not well understood how these particles sometimes aggregate. And on Earth, they all tend to sediment over time. So there's all these stabilizers that are required. Flew them on the shuttle. And so these weird structures, tree-like dendritic structures not normally seen. Some things crystallized that never, in space that never previously had crystallized. Continue to fly it and see structures that, again, you never saw on Earth, where these things would separate phase or separate from each other. The theory had it, and that was being used. It would occur in a certain condition. It was way, way off. And these things would tend to segregate far different conditions than anybody predicted. I don't expect you to read this, but Procter & Gamble is a partner in all this. As they pointed out, their products are $100 billion, 100,000 jobs worldwide. They not only are using the results from these experiments in their own product formulations, but they're using the people that we trained to help them with this, which is a really important aspect of science in general. What you learn along the way, you can end up applying very differently. And space really teaches you to think differently, which to my mind makes you a really needed commodity, if you will, out in other environments outside of space. Backstory on this one of those experiments, this is Rafat Ansari, was the project scientist who looked at the light scattering where we measured those particle concentrations. Rafat's father got cataracts. He realized that a cataract is simply a collection of particles that have come together, just like he was seeing in space. Used the technology that we flew to measure in space, miniaturized it, started applying it to see if he could detect cataracts, the formation of cataracts very, very early, far and literally 10 times sooner than any other device that existed on the market. 2003 or so, the National Eye Institute featured this device to Congress. 2009, fast forward 6 years, wasn't just the National Eye Institute, the entire National Institutes of Health cited it as one of their top 5 technology advances in the past year. The idea is to use this before you need surgery and detect the cataracts and eventually just literally put some droplet into your eye that will dissolve the crystal as it forms. If you can know that there's a crystal that's really, really small, you can use less medicine, if you will, to go after it, which is why the Eye Institute's so interested in it. Cataracts are a problem of the astronauts, as most of you know, in fact, from the radiation exposures in space. They can develop. Rafat's convinced that just simply looking into an eye, a non-invasive approach to diagnosis, can lead to glucose monitoring. There's a connection, I don't have time to go with Alzheimer's disease, but I can go into it later. But the neat part of this story, which I really like, I asked Rafat, why did he become a scientist? Okay, and he said when he was a 7-year-old in Pakistan, he saw people walking on the moon and said, that's absolutely amazing. I want to go into science because of that. They're up there for the science. So human spaceflight touches people in ways we don't expect. Fluids program, trying to know in zero-G where the liquid is and getting it to where you want it is not an easy task. This just shows a little vein spinning in here and moving liquid up and down the sides of the container. This happens very quickly, as you can see, but in reality it took about 2 hours to move this. And this is only a few inches long. But the knowledge followed that was gained followed the theory in this case, and it's been used in other shuttle experiments. This was flown on STS-77. What was learned from some of the infilling experiments, the principal investigators told me Lockheed Martin used that knowledge to extend the satellite life by making sure that the liquid, in their tanks, they could keep them in service by many more months, saving them millions of dollars, or producing millions of dollars of revenue. Another fluids experiment, this is close, not quite Hubble, but shooting something into regolith and watching how the individual particles, aggregates of particles, eventually collect with each other and how they disperse, produce several articles about the rings forming around Saturn over time. It's something I know nothing about, but in fact was one of the results. And in general, the fluids things are just beautiful to look at, frankly, the large droplets that were formed. What was funny is the PI for this particular experiment was described what about applications. This goes back to Newell's comment talking about potential. He said this was the knowledge from this would eventually help cure diabetes, cancer. I was next on the podium with our little combustion experiments, and they turned to me and they said, what good are your experiments? And I came really close to saying, we're going after hemorrhoids. But I didn't. You have no idea how hard that was not to. And just said they're science experiments. That's all they are. And it turns out, like I said, 18 years later, I never thought I'd know where these things would end up. Materials, the liquid phase sintering materials experiments. I'm going to just highlight 3 materials experiments, well, one of which affects the metal cutting industry. And I'm sorry I'm going back and forth in front of you guys. Sintering involves collections of particles that you heat, and you try to eventually make them much more dense, get rid of all the void space. They go through a liquid phase. The idea is to have them form in such a way that you don't need any machining afterwards. Okay? Unfortunately, you always do need machining afterwards because the precision just isn't as good as you can make with machining. The idea was to do, of a professor, was to do this experiment in zero-G. One of the things that happens in 1G is you get all these buoyant convection cells going. So it was clear that this was going to produce an experiment with much less distortion, much better compaction in zero-G. In fact, it turned out to be exactly the opposite. Far more distortion, far bigger problems, and it showed that the entire theory was wrong. It was owed to surface tension-driven flows that had not been fully accounted on Earth. The company, Kennametal, this is a $25 billion a year industry of just some of the metal cutting tools. The company that monitored that experiment ended up changing the way they make their materials from the knowledge gained, got rid of 40% of their production costs because they don't need to machine them anymore, because they were able to change the way they actually do the sintering. And once again, they hired the Penn State students that did the experiment to join their own workforce, and those people, in fact, won Innovation of the Year like 2 years later for the entire company. Second experiment, one of the big things in material science, today's computers can do absolutely amazing things, so you don't need to do as many experiments, but all those depend on the proper knowledge of things like thermal conductivity, diffusion coefficients, the properties. The space experiments where we allowed solidification to take place, this was one called the isothermic dendritic growth experiment, got at those thermophysical properties that are now international benchmarks. So everybody, every metallurgist that does this kind of casting solidification uses the data that came from these experiments. They're just, again, pretty pictures. Similarly, flue experiments, glass forming, metallic alloys. Yes, that is a golf club. The liquid metal golf clubs that people have used came directly out of the experiments flown on the shuttle. This is nowhere in the back can you see what's going to happen here. Apologize, but 3 different tubes dropping a ball of them. The metallic forming alloy, I don't know if it goes up and down. This ball in the middle, well, the others died out after about 10 seconds. This thing keeps going for like a minute and a half. Okay, so which is why on these golf clubs you get so much of the energy returned to it, and the ball actually goes further. The Defense Department also took notice of the energy return, and it's used in armor penetrating artillery shells. All right, I don't know how I'm doing on time, but I'm going to go fast. Protein crystal was what started everything. A lot of experiments were done. Our bodies are full of many, many proteins that serve all kinds of biological functions. To design drugs as well as to reduce disease, you really want to know what the structure, the molecular structure of those proteins are. Today, again, because of computer advances and, frankly, advances in X-ray sources, you need smaller crystals. But when we were doing these experiments, you needed bigger crystals as well as well-ordered crystals to shoot an X-ray beam through to get the proper diffraction pattern to back out the molecular structure. So you could find the active sites where you want to place a drug, for example. So the whole notion is to do structure-based design. And more than any other type of experiment, these flew over 50 times, 50 different shuttle missions. And the pictures between Earth and space, they were bigger, better ordered sometimes. I'm just going to leaf through these. Insulin. You talk about setting expectations. The very first time these flew in bulk, the headline of a local paper of the PI said 43 out of 48 samples fail to crystallize appropriately. Meanwhile, the PI was jumping up and down that 5 out of 48 worked because he never expected that would happen. And on Earth, rarely do you get that kind of success rates. And so it's, again, managing the press, managing the expectations was kind of amazing through this whole thing. So, and this continues. It spawned all kinds of industries. At this one particular technique that was used, vapor diffusion, flew on 19 missions. Again, thousands of experiments tend to get done on Earth, and the field has really evolved since then. But getting 1/4 of the crystals that you flew, producing better data than anything that had been done on Earth over many, many years is a pretty impressive result. And one thing, like anybody who's ever run experiments or tests, the more often you do it, the better the results. The more often they flew, the better the results of these things. So I'm going to just fly through these now to save some time. And all right, so I'm going to close. I haven't highlighted too much STS-107, but I want to talk about 107, Columbia's last mission, for a minute. And this one's always hard for me. But I want to talk in particular about Casey Chawla, Mike Anderson, and Ilan Ramon on this particular flight. I opened with combustion experiments. I'm going to close with the combustion experiment that happened to fly on that mission. Everybody knows how we put out fires here on Earth. You dump a lot of water on them. Oh, often the water does as much damage as the fire itself. So there is a lot of work still ongoing here to see if you can use water mists, if you will, as little water as possible in mist form to put out fires, particularly when they're small. There was a group at the Colorado School of Mines that came up with an experiment that we chose to fly on 107, in which, taking advantage of zero-G, you could literally set up a cloud of water droplets, any size you want, any concentration you want, and let it just float there inside a tube, and then light a fire of whatever strength you want and watch it propagate through the tube. And when it hit this section of the tube that had the water droplets, it would either go out, it would weaken, and in fact, in some cases, it even accelerated. So the idea was to do that kind of experiment very systematically, run something like 34 tests. Partway through the 107 flight, the pressure chamber, this tube and the pressure chamber that it was in wasn't holding pressure. And so just like Apollo 13 of the predecessors, the folks on the ground came up with what they thought was a solution with materials on board, ran to a local bicycle store to buy a bicycle pump, to come back and test their solution, and then see whether that solution, would work. They realized it would work. They wrote crew procedures to make it work. Then needed to get permission to radio up the crew procedures, find time, et cetera, in the crew timeline. Let's see, yeah, I want to go back here. So what happened then is that Casey Chawla, who was scheduled to have a half day off during then, something that those of you who work shuttle people cherish so they can look out the window, gave up her half day because she really wanted this experiment to work. So did Mike Anderson. The day before they were supposed to land, crew members get asked often, what was your wow moment in flight? What was your very favorite moment? Mike Anderson said, when we got this experiment to work. In 1/3 of the time, they did 2/3 of the tests, got 33 out of 34 experiments that were planned done. Data dumped, was able to be telemetry down to the ground, complete success. The story about Ilan Ramon, the Israeli astronaut, as you know, and who one of the crew members this time trained his younger brother to fly, who also, the younger brother recently died as well. So this flight is very meaningful to the Ramon family, the one that's flying on Friday. But Ilan Ramon had been planned to participate in the Day of Remembrance, Yom HaShoah, at the United States, at a large celebration, actually in Cleveland, Ohio, of remembrance of the Holocaust, in which 6 candles get lit for the 6 million Jews who died. And he was to come there and light candles at this particular synagogue. Obviously, after Columbia, he couldn't. The congregation itself chose to honor the memory of the shuttle crew members by lighting one of the candles in remembrance of the crew. The person who came to light that candle on behalf of that mission was one of the people from the water mist experiment. In fact, it was the project scientist who works at NASA. The project scientist is a gentleman named Suleiman Gokoklu, whose religious faith is one of Islam. Okay, so picture this is 2003, Persian Gulf War, etc. And a Muslim comes into a Jewish synagogue with 1,000 people because they are bonded together by their mutual belief in space, okay, and what space does for people. So you can talk about, this is Sule right there, and you can talk about all the practical benefits, all the wonderful science, all the incredible engineering, but there is an intangible benefit to what we do that goes with inspiration. And one of my favorite and closing quotes in all this was many years ago when Freeman Dyson, who was no fan of human spaceflight, offered the following: science is much more than space, and space is much more than science. And I couldn't agree more. Science is a part of the picture, engineering is a part of the picture. There's something much bigger in our spirits than that the shuttle has given us over all these years. So with that, I'm done. All right, thank you.